and welcome to the stream. Um, because I don't have a lot of time for this one, so I'll just get started with the actual material really quickly. But this one is done according to is per request. So if you were commented and asked about a walkthrough of the section on limit and continuity in the book by Vladimir Zorich called Mathematical Analysis 1. I have long wanted to discuss and kind of show this book, even though I can't really show it because it's still not open source. But this is a great book in the classic Soviet Russian tradition. And it's not your average analysis or calculus book because mathematical analysis is basically calculus in a Russian tradition. There's no equivalent word for calculus in a Russian university. So basically, mathematical analysis is supposed to be the first introduction to calculus by not just to math student. Actually, this one, according to my friends from Russia, is actually also the standard textbook for science and engineering students, which to me is very surprising because this book is highly mathematical, is highly, how should I say, rigorous. While at the same time, it could be argued that it is selected for those majors as well because it also covers quite a lot of applications and many of them non-trivial. So this is supposed to be a book for someone who first introduced calculus beyond high school level. Okay, and I would say it can easily rival, say, a book like Baby Rudin, and this one is much more comprehensive. So mathematical analysis 1 and 2 together are well over, or it's just classic Russian style, the classic War and Peace, your Dostoevsky kind of text, but for math, well over 1,000 pages. But enough singing praises for this one. Let me just get to the main topic. This or Spivak, very similar, actually very similar. Spivak calculus is for single variables only, but if you're interested in that kind of style, this one is much more expanded. So Spivak's calculus, by Spivak I suppose you mean Spivak's single variable calculus, right? The famous Spivak calculus, not his small book called Calculus on Manifold, which is also great, by the way. But this one is the whole package. Zorich 1 and 2 is Introduction to Rigorous Calculus and Application. But to be honest, realistically, I can't imagine this one being adopted in any kind of Western institution, because it's so huge. Because it's perhaps for university perspective they want to move students as quickly to more advanced subjects as possible. So yeah, if you really like calculus, if you really like analysis, and you find, say, Baby Rudin a little bit dry, then I would strongly recommend this one. Okay, and it's great for self-study. Okay. Yeah, I work with Jimidovich a bit, but there's just tons of problem. In Europe, general calculus similar to classes has more abstract theory. Exactly. This is a Russian tradition I was talking about. The Russians like to put problems in textbook, at least back in the days of the Soviet Union, in separate text to make things more manageable. Although this one has also tons of practices. This one by Zorich is more integrated and just a singular source. Okay, but back in the days of Soviet Union, books tends to be split it into main text and problem book. So that's why you got a Jimidovich, book like Jimidovich. And there's actually a lot of great examples of Russian-style problem books that are highly regarded. Okay, but it's inconvenient for foreigners or non-Russian speaker because sometimes only one is translated, like only the problem book is translated. Sometimes only the main text is translated, and you gotta find the appropriate companion problem book, and it's not always easy to do so. All right, with that out of the way, let's get to the main topic. Okay, I'll just get on with the actual math because I can't stay for long for this one. Okay, so we're talking about chapter 3. Chapter 3. Although this part of the introduction is, if I'm just going to give out the definitions, I mean, I have to, it's going to be a little bit dry and perhaps unmotivated. That's because a lot of the motivations were done in the previous chapter on the real numbers. But let's just talk about the limits and the notion of continuity. And I'll supply with my own commentary as well as diagrams, etc. So, definition 1, a sequence. A sequence is simply a function from the set of natural numbers or non-negative integers, sorry, not non-negative, positive integers to a set. Okay. So a sequence in a set X is a function. That's the formal definition of a sequence. F from big N to X. Of course, informally, you can think of this as an infinite list. Okay. Yeah. Tau and Albert, exactly. Those are very good. I'm personally very much influenced by Abbott. I didn't have the chance to read Tau's, although Tau's measure theory is very cool. So that's a sequence. So basically, if we draw a diagram, it would be this is big N, this is X. Big N is 1, 2, 3, and so on. In the analyst tradition, we start big N with 1. Okay, and it maps to F1, 1 maps to F1, 2 maps to F2, 3 maps to F3, and so on. This is a sequence. Okay. These are called terms. F1, F2, F3, these are called terms of the sequence. It is often that we write notation. Often we write xn equals f of n. That's it. Okay. So just the formal definition when we actually do problems and whatnot, we tend to write xn. Okay. So most of the time we'll be dealing with only sequences of real numbers. So if we just say let xn be a sequence, it means sequence of a real number, okay? Although the notion of sequence can be generalized to more abstract spaces. Okay. So next up, definition of limit. So actually we covered the definition of limit of a function near the end of our intro to proof session last week. Okay, but we're going to review the idea and what exactly we're trying to capture. But this is the definition given by Zorich verbatim. Okay, it says a real number A is called the limit of a numerical sequence xn is the limit of a numerical sequence xn if for every neighborhood VA, okay, I'm going to review that notion. What is a neighborhood? If for every neighborhood VA, same notation as in Zorich, of A, there exists an index big N. Depending on the neighborhood. Okay, so big N, for every neighborhood big A, there exists a big index big N, which can depend on VA, such that all terms of the sequence having index larger than N belong to the neighborhood VA. Okay, so this is a purely verbal description. And it's a good exercise to translate this description into symbolic logic statement. And this is actually, I strongly recommend readers of mathematics do all the time, is to translate statement or express statement in equivalent fashions as many forms as possible. Right. So this way, it's a great way to avoid rote memorization and actually understand what the statement is saying. So try to say the same saying, just in different ways. It's also a great way to internalize the definition. So basically here, what we're saying is, let me just finish writing this sentence, belong to the neighborhood, belong to VA. Okay. So what is this? Okay, let me draw a picture. Okay, so this is perhaps more easily visualized via a Venn diagram rather than the straight line, because straight lines gets clouded really easily. It's one-dimensional. But if you prefer a line, okay, I'll do that as well. So let's first look at the Venn diagram situation. So let's suppose this is R. Okay, this is a set R. This is R. So okay, so the neighborhood is an open set. Recall, every open set has this form. So VA is just A minus epsilon, A plus epsilon. Also known as an open ball. Okay, so basically, it's just A with a little bit of a wiggle room to the left and right. That's the neighborhood. So we're going to use a circle of a circle centered at A to represent the neighborhood. This is VA, and you have a point A. This is the limit, right? This is the definition of limit. A is supposed to be a limit. So how can we understand this? It says, for any such neighborhood VA, there exists an index big N, such that all terms of the sequence, namely xn, having index larger than n, are all in VA. So n is the threshold after which the sequence members are all in this neighborhood. So this xn is in here, xm plus 1 is in here, xm plus 2 is in here, and so on. Here n may not be the exact cutoff point, the cutoff index where terms with index less than n are outside. Okay, you know what I'm saying? It just guarantees that when the index is greater or equal to n, the sequence members must be in here. Must be inside the neighborhood. You can have x1, x2, etc. outside. It might be the case that xn minus 1 is outside, and xn is inside. Now, so n is the critical index where that change happens, but it doesn't have to. What matters is after so for all little n greater or equal to big N, the sequence members are all inside the neighborhood. And you can do this for arbitrary neighborhood. Okay, this is of course a very formal way to describe limit. Okay, but the idea is very simple actually. You want to control the error. So the whole definition of limit and the continuity, etc. The idea is really just that simple. It's called error control. And it's an idea we use in all areas of science and engineering, and also sometimes in real life. It's error control. So suppose you can consider the sequence as an approximation device, an approximation scheme for the number a. And we do this all the time. Like pi is an irrational number, right? It's the exact value of pi is not known to anyone, right? The exact value of pi is hi Levi, yeah. So the exact value of pi is not known to anyone because we only in practice work with the approximation of pi, right? However, for engineering practices, for scientific applications, right, you want to calculate a result, say the area of a circle, to a certain accuracy. So you can think of the decimal expansion of pi as a sequence, right? Because 3, that's the first term, 3.1 is the second term, 3.14 that's the third term, 3.141 is the fourth term, and so on. So in practice, we're interested in, say, how many digits I need to achieve a certain accuracy. And that's exactly what we're doing here. Right. So given a VA, that is an error tolerance threshold, you want to know how far you need to go down the list so that it's sufficient. So it's sufficient for the accuracy requirement. Okay, so that's the Venn diagram picture. I'll just draw the other two visualizations real quick. This is visual 1. A visual 2 would be just a line. Right, so this is here you have a point A. This is a big neighborhood. Okay, this is a big neighborhood, but the idea is this is VA, okay, and xn is here, x big N is here, x big N plus 1 is here, perhaps x big N plus 2 is here, and whatnot. Okay. For all xn with little n greater or equal to big N. And in fact, I'm not even going to bother putting the x1, x2 on the axes because they don't matter. What the limit definition cares about is what eventually happens. Okay, it does not care about the behavior of the sequence for finitely many terms, no matter how great that number is. Okay, it can be, say, x 10 million is outside the interval, we don't care. It cares about what eventually happens in the sequence. So that's a second visual. And the third visual would be more like a scatter plot diagram, like an actual function of a graph, actual graph of a function. So this will be the natural number. This is the real numbers. So this is A. A neighborhood of A can now be visualized as a tunnel. A strip, horizontal strip on the plane whose center height is A, and A plus epsilon, A minus epsilon are the error tolerance thresholds. Okay, so this is saying that, let me just put a sig dot here. So after a certain index, critical index, every point, not necessarily critical because I'm saying this before big N. Okay, when little n is less than big N, we don't care. What we really care about is after and equals after big N, all the sequence members falls into that Arrow's threshold. And before, it can be inside or outside or inside or outside, inside, outside. We don't give a damn. Okay, so that's basically the definition of limit. And of course, you need a lot of practice to work with the definition. And one of the trickiest things is to show the existence of big N. And usually that requires some kind of scratch work. And in the actual proof, you would just give the big N and verify the big N quote-unquote works. So the proofs can be rather confusing for beginners because they probably don't know that the big N given in the proof is found on the scrap paper, which is not shown to them. Okay, so that's the definition of limit. And as I was saying, there are equivalent ways of saying it. Let's, for example, write it in the form of symbolic logic. Right? Symbolic logic. So equivalently, the limit n tends to infinity. I know there are people who hate a lot of symbolic logic symbols in the textbook and whatnot, but undeniably, they can help you analyze a statement, and especially when it comes to the order of quantifiers. So at some point we will do a live on uniform convergence in particular. The difference between pointwise and uniform convergence can be appreciated in many ways, but one of the ways is that it's just a matter of switching the location of quantifiers, and the meaning got completely changed. So let's write the quantifier version, a quantified statement version of this definition. What is the limit? What is the statement? Well, limit of xn as n tends to infinity equals a me. This is defined as, by the way, this is in Zorich, for all neighborhood, for all VA, there exists a big N in the set of natural numbers such that for all n greater than big N, actually if it's greater than actually larger, so I need to change my picture a little bit. I need to remove the xn from the circle. This is not guaranteed, right? So actually, yeah, I thought it was greater or equal to because I'm used to that definition, but here, if we're really being literal, so we should it should be xm plus 1. That's inside. We don't know about xn. Okay, so this is, yeah, that's the picture. Okay, and you have xn belongs to VA. So that's the quantified statement. The advantage for that is rather brief, but you need to decode it. And it's also a great way to analyze. It's also a great way to analyze a statement, right? So to ensure the verbal description is precise. Right? Okay. So another verbal description would be as follows. For every neighborhood VA, actually, every neighborhood of VA contains all but finitely many terms in a sequence. Let me just put that down. Equivalently, every neighborhood VA contains all but finitely many terms of the sequence. All but finite. That is to say, except for possibly finitely many elements, everything is in VA. Every term is in VA. All but finitely many terms in Xn. So that's the equivalent description for that. Okay, and because VA can be parameterized by epsilon, is also equivalent to the following, which is for all epsilon greater than 0, this is a classic version, I believe first formulated by the Czech or Bohemian mathematician, Bolzano. So, not Cauchy actually. The original definition is due to Bolzano. There you go. Okay, so that's the equivalent way of writing the definition. There's a bunch of notation. Okay, there's more notations. For example, xn with an arrow to a. And this is called, it said xn is convergent. I would say xn is convergent. If it doesn't have a limit, then yes, in Bolzano-Weierstrass. This definition of limit, the rigorous definition of limit, is due to Bolzano. If xn does not converge to a for all a in real, we say xn is divergent. The divergent simply means not having a limit, aka not convergent. All right, so that's the definition of limit. And to work with this, you typically, as I said, you need to do some scratch work. And we'll do two examples. Okay, we'll do two examples. One would be working with a concrete sequence. Another one would be proving a property of a sequence. Okay, so there you go. Example, and this is example from Zorich. Example here. Example. Let's just do a simple example. There's no need to go crazy here. Just say example 2. This is example 2 in Zorich. The limit of n plus 1 over n is 1. Okay, simple as that. Not everything has to be super non-trivial, and yeah, so this is just a quick illustration of the principle. But let's try to prove this using the definition, even though it's very simple. But it outlines our strategy. So, as we were saying in the intro to proof notes, actually, let me just pull that out. It's a Cauchy from, I believe it was Bolzano. Okay, Cauchy, of course, extended it in a great way and did the kind of systematized analysis. But the definition, original definition, is epsilon delta epsilon big N is due to Bolzano. All right. So here, we mentioned this in our intro to proof video. So the general strategy for finding a proof is as follows. And this can even work even when you don't know what the heck are you trying to prove. You simply look at the logical form of the statement and you can write the corresponding scaffold or the outline of a proof. Proof writing is, generally speaking, not linear, in the sense that you write down the first line and then the second line, as if calculating an integral all the way to the end. It doesn't typically work like that. Instead, it requires kind of a back and forth between the assumption and conclusion. So, the first thing we wish to do when it comes to proving a statement is to analyze its logical structure. And the whole reason we spend a lot of time on connectives, quantifiers, is to be proficient with spotting the logical structure. Is this, for example, a statement with for all, or there exists, right? If you want to use a direct proof, for all x, px is a predicate, is a property of x. If the statement looks like this, you start with let x be an arbitrary but now fixed element in the universe U, which of course can be simply written in a shorthand form, say let x in U. So let x in U correspond to this quantified statement. Okay. So for example, let's say the statement looks like for every x is a widget, and you don't even know what the definition of widget is, or is there any results or theorems that leads to the conclusion that x is a widget. You don't know. But based on the structure of the logical structure of the statement, you can simply start with the sentence let x in U and move on from now. Or just sometimes follow your nose, as Terence Tao put it. Right? And that's the this is something that should be done like automatically, because it requires zero thinking of the actual content you're trying to prove. You can just write down the starting sentence, right? And the second case, or not the second case, but the second quantified statement would be, of course, existence. To prove existence directly, you need to pick or actually choose the x that satisfies the property, and the proof for that would be start from your choice of x and verify it actually works. Okay, so this is very much in the quote-unquote constructivist spirit so of course, speaking of constructivists, they're very active on the internet, and of course sometimes they're very they're very opinionated towards about their views and whatnot. I mean, it's not necessarily a bad thing. I just like to say that from my personal observation, all mathematicians are part-time constructivists. We prefer explicit construction. It just feels more satisfying. Right? If a statement is there exists an x blah blah blah, whenever possible, we wish to give an explicit construction. Of course, this is preferred. But for much of the mathematics, if you take that preference too seriously and demand everything claimed to exist, to have an explicit recipe for that object. If you do that, then you make your life very difficult. So instead, we are happy with, mainstream mathematicians are happy with saying, oh, to prove existence, it is also okay to take an indirect route. That is to say, assuming such objects don't exist, and we get a contradiction. And that's also okay. But here, this is a direct proof, okay? This is why I was saying, regardless of a mathematician's own philosophical inclination, we're all part-time constructivists. Nobody is denying that an explicit construction is more satisfying. But the reality is, if you really take that too seriously, as kind of the life and death principle, or you know what I mean. If let's say I mean, of course, the constructivists would argue if something that doesn't have explicit recipe, it's not even a proof. Okay, we don't go down that route, but of course we prefer, whenever possible, to have an explicit construction. So Oh, hi Tep. Thank you very much for joining the stream. This week I didn't have much time to do the Russian exercises, but hopefully we'll do more math. Not more because I'm busy with other things. I'll try to stay connected with my audience. But this one is upon request actually. So as I was saying, look at the logical structure. We can write down the necessary outline for the proof. And now it's just a matter of filling in the blanks. Guys, I was just watching another math channel yesterday, previously known as JC Practices Math, now known as Math Can Be a Hobby. He was covering proof by induction. He was covering proof by induction. And also induction has a very nice outline as well. Induction proof also has a very nice outline as well. And to write down the outline, you don't even need to know the actual strategy for getting the proof done. Right? So here we're just going to follow the logical quantifiers and do the outlines first. Okay, for all epsilon greater than 0, for that let's start with, I'm going to actually use a different color. Okay, start with let epsilon greater than 0. This is just to see how much things we can do without even knowing the actual proof steps. Right. So let epsilon greater than 0, and now because it is now followed by an existential quantifier, we need to write pick something. Pick big N to be something. So this is a fill in the blank. Okay, and now after that, it is now followed by another universal quantifier. So you let little n to be greater than big N. Okay, and now here it is followed by steps that actually shows xn is in a VA or xn. Hang on a second. It should be. This is a little bit awkward because epsilon is not used. So I'm just going to write it as the distance between xn and a to be less than epsilon. Which is totally equivalent to xn in VA. So this is what we're trying to show. All right. So we're trying to get to xn is in VA, or xm minus a. Here, what is a? You can read it from the. First of all, what is xn? Xn is just m plus 1 over n. Okay. Yeah, Levi, thank you very much for mentioning this. Actually, I was planning to host some kind of a talk with perhaps Leo or someone else, as me seeking advice on how to get into Lie theory. So, because he knows a lot more, and also JC, they know a lot more about algebra than I do. And I don't know, is there some kind of a bridge course? So for applied mathematician to get into Lie theory, right? Because it's a really exciting field, and of course, Lie theory traditionally has a high barrier of entry. Okay. Anyway, coming back to the main example. So here, what we're trying to get to, right? So here in our example, you should. Let me just write it on the side. Okay. So recall the definition for that is for every epsilon greater than 0, there exists big N in the set of natural numbers, and then for all little n greater than big N, absolute value of xn plus 1, not xn, but n plus 1 over n minus 1 is less than epsilon. Right, so at the end you should have n plus 1 over n minus 1 less than epsilon. And after that's done, you can finish up with a conclusion. Therefore, by definition of limit, the limit of n plus 1 over n as n tends to infinity is 1. So now it's just a matter of filling the blanks. And to do that, we typically adopt the strategy of working backward. And this will be also emphasized in our Intro to Proof series. So by that, we mean assuming the conclusion in your Scratch work, and try to find the appropriate n. Right. So yeah. So let's start from assuming the conclusion. N plus 1 over n minus 1, absolute value less than epsilon. And of course, we just need a sufficient condition for that. So here in the big box here, we wish to do a sequence of deduction that leads to the inequality that we wanted. So here we're just looking for sufficient condition for this one. We don't have to be, so to say, do if and only if every step of the way. What you really only want is a sufficient condition for this to hold. So here on the left hand side, this is just 1 plus 1 over n minus 1. So that's just 1 over n less than epsilon. Okay, 1 plus 1 over n less than epsilon, and this is actually equivalent, but also but you can just write implied by 1 over epsilon less than n, or n greater than 1 over epsilon. And that's exactly what we wanted. Right? We want a critical threshold. We want a critical threshold for big N, so that or actually, it doesn't have to be critical. The critical would indicate less than big N, the statement is not true. After or greater or equal to big N, the statement is true. We don't have to be that strict. Okay, you just need a big N so that everything works out. Okay, so so the idea is to pick big N to be close to 1 over epsilon. So this is our choice of big N. Okay. All right. So here, pick big N. Okay. Thank you, Levi. Thank you very much. And hi, Ego. Thank you for joining the stream. So based on this Scratch work, we can just say, pick big N to be big N in the set of integers, so that, in fact, let's change the position of the blank. You always have big N in the set of natural, such that n is greater than 1 over epsilon. This is always possible, and sometimes it's also a great idea to justify why this is possible. And this is because of the Archimedean property of the reals. It's a property of the real numbers. The property of the real numbers, the defining property of real numbers, aka the completeness axiom, guarantees that the real numbers contains the set of natural numbers. The natural numbers is unbounded. The natural number is unbounded in a set of reals. So the very existence of big N, that is to say, you can pick a natural number to be as big as you like, to be greater than any threshold, to be greater than any real number. You can always do that to any chosen real number. Okay, it's impossible to find a natural number to be greater than all real numbers. That's not possible. Otherwise, the set of real would be bounded. That's not true. I'm saying is for any given real number, it is always possible to find a natural number that is greater than that. And this is by the Archimedean property. How do you spell Archimedean? Geez, can't spell. Feels right. Archimedean property. Okay, This is just a nice justification, which I strongly recommend putting, but you can't get away with. If you don't write that, I don't think your calculus teacher would go crazy and deduce your mark. Okay, but this is just a nice justification. So now the n is chosen. It's just a matter of verifying that the n works as the big N in the definition, right? We want to show that all terms of the sequence having index larger than n belong to the neighborhood. So starting with little n greater than big N, this is already part of the outline. And we wish to work our way backward to get to this, work our way forward this time to get to the conclusion we want. Okay? No assuming the conclusion in the actual proof. In a scratch work, this is okay. But you always want to make sure the logic work in reverse. Okay, so because n is greater than big N, you have 1 over n is less than 1 over big N. Right? And since big N satisfies this inequality, this is by our choice of big N, this is less than epsilon. And then you can put an absolute value sign, say 1 over n absolute value less than epsilon, and write and put a +1 and -1. And this completes the proof. So this is a classic proof. It's a classic proof of working with quantifiers, work backwards, and then write the proof forward. Okay. Awesome. Thank you very much. Thank you very much, guys, for recommending literature on Lie theory. We should have a live session about that. How to get into Lie theory as a beginner. Perhaps do some actual Lie theory on live. Okay. It's a great topic, and I believe it's now well understood among applied scientists that Lie theory is useful. I believe most of my community is applied. Well, big surprise, perhaps, and they want to get into advanced mathematics, often topics with traditional heavy barrier of entry. And I think Lie theory will be a great topic for discussion. Yeah, so that's a really basic proof, but it highlights all the necessary strategy. It looks easy because of the scratch work only involves rather simple algebra. The thing is, the structure of a more complicated proof, which we'll see next, is very much in the same format. You just need to do more scratch work. It just makes your head spin. Okay, as a final check, make sure all the ingredients in that corresponds to the definition are present. Let epsilon greater than 0. That's 1. The first quantifier. Pick big N. This corresponds to existence. Let n to be greater than big N. And finally, the conclusion. So we're done. Okay. It's always a nice idea to end the proof with a concluding sentence and not just, oh, less than epsilon, and you're done. It feels kind of awkward. Put a nice little concluding sentence at the end. Finish up with a QED or a square, most satisfying. Okay. No worries. Thank you very much for requesting the stream. I mean, this is very important, right? I've been doing things like measure theory and whatnot, and I got feedback on my Discord saying because they don't have the background in analysis, they have found it difficult to follow. So I figured, you know what, let me just do kind of a bridge course. Intro to Proof is episode 1, and We finished up the intro to proof episode 1 with definition of limit of function, and now we're going to do it again using Zorich's exact word, and this is the follow-up. Right. So my objective for the intro to proof is very much a rapid-fire, single-minded mission of helping people to get into a rigorous text on things like analysis, topology, differential equations, probability, as much as possible. So it might be an imbalanced project because I don't really care about the discrete side of things, a discrete mathematics kind of thing. But I do believe a lot of the proof techniques are similar. Because of the language of mathematics, the language of mainstream mathematics is fairly similar. Right? So I think for example, the proof strategies outlined here can be also adapted to, say, algebra, although the actual filling the scratch work would be very, very different. Analysis tends to work with inequalities a lot, whereas algebra work with equality. So there's that. Okay. Yeah, thank you guys very much for the nice comments in chat. And now let's look at a more complicated example. So example two, actually it's not an example, but rather a theorem. Right. So let's prove this theorem, which is also well known in elementary analysis. This is theorem 2 on Zorich page, page 20, page 82. This is theorem 2, page 82, Zorich. This is a more complicated example, but as you will see, you can still just write down the outline of the proof and then try to figure out the details. So let xn and yn be sequences such that the limit of xn is big A and the limit of yn, n tends to infinity, is big B. So this is one of the limit laws. The second limit law is the product law. The limit of xn times yn as n tends to infinity is A times B. Right. And part C, the limit as n tends to infinity xn over yn is A over B, provided yn is eventually non-zero. Non-zero and B is non-zero. Okay, so that's the law we try to prove. So now, because we don't have a concrete expression like what we have earlier, n plus 1 over n, right? So we need to work with the definition of the of limits abstractly. Okay, so starting from the premise, right? You have the two limits a and b already. So some sort of epsilon big N statement is already provided, and you want to manipulate the epsilon and big N to get to the conclusion that you actually wanted. And once again, so why don't we just write down what we can already do? Okay, the outline, the existing definition, and whatnot. Okay, and then tweak things later. Okay, so sometimes you see this sort of really rather clever choices of big N and delta and all those fancy symbols, and wonder why the heck is this chosen, or how on earth am I supposed to figure that out myself? That's usually not a big deal. You can always start with a generic choice and deduce forward and tweak your choice later so that everything looks nice. It's less than an epsilon, not less than a 2 epsilon, for example. You can always tweak those things. not a big deal. Right? So the idea is, so suppose xn can get close to big A, yn can get close to big B. How can I make xn and yn close to A times B? Yeah, analysis uses inequality and bounds everywhere. Exactly, and in particular triangle inequality, right? Arguably, the number one inequality in analysis, just triangle inequality. Are you going to compete entire Zorich complete? No. This is very much a singular request. As I said, this is meant to be part of the bridge course on proof writing. My point is, if you just know basic logic and set theory, much of the mathematics, like even quote-unquote advanced mathematics, is already accessible. I'm not going to do the whole of Zorich, even though there's many great examples in Zorich, our video and live stream material. Zorich is really awesome. So yeah, what else can I say? Mathematical treasure. Anyway, so how do we prove these? So first of all, let's just follow our previous success. Okay, let's gonna write down the template. Okay, what does this mean? What does this statement mean? The limit of xn times yn equals ab. Of course, this just means for all epsilon greater than 0, there exists big N such that big N such that for all little n greater than big N, xn yn minus ab absolute value less than epsilon. Okay, so yeah, so let's write these things down in a green pen. This is the outline. So let epsilon greater than 0. Just leave it at one line, as if it's like a one line of code declaring a constant. And you pick big N. So the thing is, big N is unlikely to have a formula because xn and yn are general. So what is most likely to happen is that big N is related to the big N, quote unquote the big N, in the definition of limit of xn equals a and the limit of yn equals b. Because you are given two limits, so you're given an epsilon big N statement for each limit, and the choice of big N in our main proof for establishing xn times yn equals ab, this big N is likely related to the big N here. It's a natural thought, right? So so that's why I'm leaving space here. So we're given it's not part of the template, but we're going to use the assumptions such that blah blah blah. Just leave it here. Okay, and now let little n to be greater than big N. Do the deduction in a big box and reach the inequality that you want, which is xn minus xn times yn minus a times b absolute value less than epsilon, and finish up with a conclusion. Here, straight. Finish up with a conclusion and say, by the definition of limit, the limit of xn yn as n tends to infinity, so that's equal AB, right? So that's the template anyway. It's very similar to what we did earlier for the simple formula case, right? And now let's just unpack the assumption. Okay, so well, just write it down. Write the definition down. The given since limit of xn n tends to infinity is big A. by definition, for every epsilon greater than 0, there exists big N. Big N, let's call it big N. Yeah, call it. This might need to be changed, okay? We don't know. We don't know what choices of epsilon is helpful, what choices of big N is helpful, but that's okay. The point is we want these ingredients ready and be used whenever we want to. Xn minus a absolute value less than epsilon. And since I don't like analysis, you know what? I'm not a dedicated, die-hard analyst fan either. I'm an applied mathematician. It's just that traditionally analysis is more connected to application, for the most part, of course. When I first took real analysis, I despised it. Although I love complex analysis because it's closer to calculus. That's my calculus brain. But later on, it's probably safe to say that I benefited from real analysis more than any subject I took. So, yeah. In grad school, I wasn't a huge fan of measure theory or functional analysis either, but you have to use it to do probability and PDEs. So there's really not much choice there. I kind of just picked up analysis along the way and didn't quite enjoy it until very late in my university and grad school career. So you just have to use it. And I suspect this is the same for a lot of people. They treat analysis or just pure math in general as kind of a means to an end. I mean, I've went through that stage, even though nowadays I often advocate there's no separation between pure and applied mathematics. So, how do we pick this big N? Well, it really depends on our final goal here. So let's try to manipulate the final inequality. So we have xn minus a absolute value and yn minus b absolute value, and we wish to connect. So this is what we want, and this is what we wish to connect. And the epsilon at the end don't really matter, in the sense that they don't have to be the same number. They don't have to be the same number. They don't have to be the same epsilon. They're just arbitrarily small values. So what we really care about is how do we get an inequality of xn minus a, yn minus b to xn times yn minus ab. So this requires a little bit of an algebra trick, as we can probably expect. So this is our given, right? Given is just what, right? Xn minus a absolute value is small. Okay, and yn minus b absolute value is small. You want xn times yn. Yeah, complex analysis is awesome. Complex analysis is awesome. It's beautiful, it's surprising, and it's applicable, and just great. Anyway, coming back to this, right? We want xn times yn minus ab to be small. So this is the product, so it's natural to try, say, multiply xn minus a and yn minus b, and see what happens. So let's try to expand this. So this way you get xn times yn minus, all right, you got b times xn minus a times, wait, hold on a second. Is it? I want a minus sign, but this is plus sign. You see, if I expand this, I get a plus sign, plus AB, which is not what I wanted. Huh. this is not, I don't like this. I don't like this because this gives me a plus sign. I don't want plus sign. Yeah, I mean, Steve, I love analysis now, but in my little applied brain, when I was doing my undergrad, I just want to get over real analysis as fast as possible. Because, well, it's hard, first of all, and it doesn't seem to be terribly related to what I do until I realized it underlies everything that I do. Okay, so that's a great paradox of learning foundational math. Anyway, so this doesn't seem to work very well, even though it's very natural. So what else can we try here? Okay, so what else can we try here? So let's try something like this. So you have, say, by the way, this is not the proof in Zorich, okay? This is just a statement there. I'm just trying to prove it myself. I want to give the process of discovering proofs. Okay, so here you have xn, yn. How about we move forward, huh? How about we move forward? So let's say xn, yn minus ab, absolute value. This is our second attempt. Say xn, yn. Can we do it like, say, a times yn? Because this way I can cook up a factor xn, xn minus a. I know xn minus a is small. Okay, absolute value, not absolute value, but then plus, say, a(yn) minus ab. This is also another common trick, right? You might wonder, oh, I use a times yn. Can you use, say, b times xn? Sure, you can. You can also multiply by bxn. It also works. Plus or minus bxn will also work. So this is very much a trickery. It takes a little bit of a trial and error. So you get xn minus a times yn, and then plus, all right, a times yn minus b. Right. So, and then use triangle inequality. This is xn minus a absolute value times yn absolute value plus a absolute value yn minus b absolute value. So that's nice because we know xn minus a, this is small. Yn minus b, this is small. And what about yn? Yn is bounded. Well, this is a result that we didn't prove, but it's in the text and it's also well known. If a sequence is convergent, it must be bounded. Now, this is what we need. And of course, a is also say, of course, is a finite, and we just wish to cook up a nice epsilon, less than epsilon at the end. Right? We know these are small. You have the freedom to choose, okay, with how small you want, but at the end you want to make things look nicely, and it reads like less than epsilon. For example, here, why don't we let, say, the upper bound, oh, no, sorry, the bound for yn to be big M. So yn absolute value is less than or equal to big M. This big M must exist. And let's just going to pick xn minus a absolute value to be less than epsilon over 2m. So this way the product is now half epsilon. And we do the same for yn minus b absolute value. We want it to be less than, say, epsilon over 2a absolute value. Yeah. This way you also cook up a half epsilon, so everything together combines to epsilon. So this way the proof finishes nicely. So now we know exactly what we need, and we can modify the beginning of the proof. Okay. Remember what we want. We want xn minus a absolute value to be less than epsilon over 2m, but you need to define m. So let's start with the boundedness of yn. right? So yeah, that's why this process is perhaps more involved. I mean, definitely more involved than the previous example, right? And if you've never seen a scratch work, even if you can understand every step in the deduction, you would have little clue of actually how you actually proceed yourself, discover it yourself. So, let's start with, since yn is convergent. Why do I see this is so freaking weird? The mouse is not the same place where I clicked. Overall, I love OneNote. I love it. It's a fantastic app. But I don't know. You see, this is weirdness. So since yn, first of all, since yn is convergent, first of all, let's say, since yn is convergent, it is bounded. It is bounded. Namely, there exists a real m greater than 0 such that yn absolute value is less than big M for all n. Okay? Less than or equal, well, that's the definition of boundedness, it is bounded. Okay? And then start with, and then we can use the definition of the limit of A. In the definition, of course, we use for all epsilon, and here we can specialize. Can I move this damn thing? Thank you very much. Yeah, by definition, there we can say there exists, let's call it NA, and with a subscript A. There exists NA in the set of natural numbers such that for all n greater than big NA, xn minus a is less than what? Remember what we want? We want it to be less than epsilon over 2m. So yeah, just write that as epsilon over 2m. This is well defined. Okay, and now what we need, so here we finally need the last ingredient, right? Since yn converges to b, by definition, we want yn to be less than half epsilon over a absolute value. So we don't need the for all epsilon anymore. We just say exist mb in a set of natural numbers. I think this is a rather involved example. Okay, and b is such that yn minus b is less than what is 2 a absolute value. 2 a absolute value. So actually, you know what? This raises a question: is a 0? If you wanted, m is guaranteed to be non-zero, right? But if a is 0, then well, you don't need the second term. So we need to actually do a little bit of a casework. So because here you're dividing by a absolute value, we don't know whether a is 0 or not. Let's see if when can we do that. So here, let's do a casework. Okay, so let epsilon greater than 0. This can be a sort of universal thing. We can do that. Let's do a casework. Case. A equals 0 is easier. Where big A is equal 0. Big A equals 0. What do we need to show? We need to show the limit is 0. We need to show the limit of n tends to infinity, x and yn is 0. This is the first case. Okay, and you pick your big N, blah blah blah. You want to show xm times ym minus 0 is less than epsilon. Right? So that's the first part we wish to do. Right? And this case would not be unlikely to be known a priori, right? Unless you've seen this the scratch work, as I was saying. Here you just wanted to, let me copy this. I want the template again. I want this template for the other case, a non-zero. Yeah, by Levi. Thank you very much for joining the stream. So here, this would be the second case. Is a is non-zero. Need to show the product is AB. Right. We'll come back to this, but first let's finish the case where a is 0. So this is supposed to be easier, right? This is supposed to be easier. So you just need the first term here. You just need the first term. So you pick big N as instructed. So big N is to pick big N such that big N is what? You just need the first inequality to hold. That is NA, to be NA. Right. Or you can simplify and write pick big N to be NA. Suppose N is greater than big N, then what happens? Well, working backward. Actually, this is forward, right? We deduce this inequality forward. So xn, yn minus 0 absolute value, right? This is the same as xn, yn absolute value. But a is 0, so you can write it as xm minus a absolute value times yn absolute value. And this is less than, xm minus a is less than epsilon over 2m times m, which is half epsilon and is less than epsilon. Right. Thank you very much. Thank you very much, Steve. Oh, dentist appointment. Well, have fun with that. Hope you survive. Anyway, thanks very much for joining the stream. So as I was saying, like, this is case 1, done. I'm sure there's got to be a way that you can write things more, so to say, compactly. You can do it in one case. Right. But this is certainly valid. So this is proving a special case. This is totally a legit strategy. And now here, in the second case. So in the first case, we just need the big NA. Okay, now let's work with the second case. Oops, need more space. I need this somewhere inside the second case. Let me just put it down here, okay? I need MB now. Here, in the case where A is non-zero, you need to pick another big N, right? And based on our analysis, you need to have Ym minus B to be less than epsilon over 2a absolute value. So let's just put that here. So this is our template. We can change it wherever we want. So here, since limit of yn is b by definition, you have this. And now this is safe because a absolute value is defined. Divided by a absolute value is okay because a is non-zero. And now we pick n to be the maximum of NA and MB. Okay, we pick big N to be the maximum of NA and NB, so that both inequalities hold true simultaneously when little n is greater than big N. Okay, this is also a very commonly seen analysis. You want if you want, say, multiple inequality to hold true, right, you pick the biggest threshold, so to say, and let little n greater than big N, and you just repeat this derivation here. Okay, so xn yn minus ab quantity is xn yn minus ayn plus ayn minus ab. So the first two has a common factor, yn. So this is xm minus a yn plus a, this is a common factor, ym minus b. And you use triangle inequality. This way, xm minus a absolute value times yn absolute value. And then plus a absolute value, ym minus b absolute value. And next we have, this is less than yn xm minus a. What is xm minus a? Well, xm minus a is less than epsilon over 2m because of what? Because of na. Because little n passes big Na, here you have xm minus a less than half epsilon over m. All right, so then times m, that's the bound for yn absolute value, and then plus a absolute value times ym minus b upper bound, which is epsilon over 2a absolute value. That's exactly how we cooked up things in the first place, which is less than epsilon, which equals epsilon. Okay, so therefore, to summarize here, xn yn minus ab absolute value is less than epsilon, and this is what we needed, as needed. So overall, summarize the two cases: limit of xn yn n tends to infinity equals ab, which is the limit of xn n to infinity times the limit of yn n tends to infinity. That's it. And this finishes the proof. And because this proof is quite long, so it's a good idea to start from the beginning and read your own proof, because we don't want to, say, have undefined symbols. We don't want to, say, use a symbol before it is defined, that kind of thing. You know, just overall soundness. Okay, so start with the fact that yn is convergent, it is bounded, so can introduce big M. In the next line, we use big M. We use the big M and the definition of limit to specify NA. So if you've never done this, you've never seen or done this scratch work, even if you can follow, indeed this is convergent, so there exists big M, there's the limit, but you would have very little clue of why we choose, say, epsilon over 2m. But once again, this is unimportant, remember. This is unimportant. What's important, this is set up simply to make the final result looks nice. What's important is, given xn minus a small, yn minus b small, you want xn times yn minus ab to be small. This particular choice, epsilon over 2m, is not critical. Is not critical. You can, for example, you can split the final epsilon in a different way, and it wouldn't matter. Okay, so and because, so here is the template, right? Let epsilon greater than 0. We want to show there exists big N such that when little n is greater than big N, the distance between the sequence and the proposed limit is less than epsilon. Right? So which brings us to this piece of scratch work. Right? So here, if A absolute value is 0, or just simply A is 0, things are actually a lot easier, so let's do that case first. And when A is non-zero, you got the second case. Same format, same template, right? So there's that. Okay, so this is a significantly more involved example. This is a big theorem after all. All right. So to prove C, you only need to prove the reciprocal law. Right. So you only need to show the limit of 1 over yn is b is 1 over b. So this will also be a nice exercise to do part C. So because of proof of B, because I only have, say, half an hour left, because I need to leave at 9, I'm going to leave C as an exercise, even though you can't find it in most textbooks. But it's a good exercise. You do the scratch work, follow the template, and if you want, you can send your proof to my Discord. I'm not saying I'm not going to grade it, but provide my feedback and see how I feel about it. Okay, do you have all the necessary ingredients? It's a nice exercise. Okay, because I want to talk about continuity now. So continuity. Continuity would be chapter 4, continuous function. This is also a very deep concept. It can be approached from multiple angles. Not angles, but multiple level of generality. That's what I'm trying to say. A continuous function. What do we mean by a continuous function? So here you have the next topic, right? Next topic, continuity. Continuity. The notion of continuity has even more ways more formulations than limit. Okay, even at an introductory level, chapter 4, continuity or continuous function. So what's the idea here? Well, the idea for the limit, as we said, is what? The idea is error control. Think about a sequence as an approximation device. You can control the error. And what would be the heuristic idea of a continuous function? Continuous function, the idea is if the input changes a little, the output only changes a little. That's it. That's it. Okay. That will be the first introduction. That's first in idea. If the input changes a little, the output changes a little. Okay. But if we borrow, say, the idea of error control, say if you want the function value to change by a little, okay, you can always achieve that by changing the input with a sufficiently small amount. It doesn't have to be an arbitrarily small amount. Let's think about that. So let's say if the function is very flat, and this is a, this is f of a. If the function is very flat, right? And if you just want f of x to be close to f of a, and because the function is very flat, it doesn't change a whole lot. It doesn't change at a very steep rate. So it is possible that even when x is kind of far away from a, f of x and f of a are still very close. And of course, you got the opposite scenario where the function is very steep. In that case, x really needs to be super duper close to a so that f of x satisfies the error criteria. Right? The error is satisfied the error tolerance. So my point is, what we really want is to have f of a to be really close to f of x. We want these two to be really close. And we don't really care whether x is super close to a, as long as it is sufficiently close. So that's the idea. We want, the idea is f of a arbitrarily close, even though this diagram is kind of basic and not very pretty, but I'm just going to leave it here. Idea is f of a arbitrarily close to f of x if x is close enough. X doesn't need to be arbitrarily close to a, is x is close enough to a. So that's the idea. All right, so with that idea, we can formalize things this way. Definition. Okay, so let's suppose f is a real value function defined in a neighborhood of a point. So a function, this is definition 0, okay, 4.1.1. Continuity of function at a point. A function f, this is Zorich's exact word, or translated. So f is continuous at the point A. At the point A, if for any neighborhood not of A, but rather FA, yeah, for any neighborhood of FA, in the neighborhood V of f of A, of f of A, there exists a neighborhood called U of A, for any there exists. This is such a common format in analysis. It is used throughout across subjects. Differentiation, integration, continuity, sequence, you name it. For any there exist. Yeah, so now for any neighborhood fa of the function value fa, there exists a neighborhood ua of a. Of ua of a, what? Whose image under the mapping f is contained in fa. Now, once again, quite a difficult definition. Let me just draw the Venn diagrams and graphs and whatnot. Beside this chicken scratch, to illustrate the notion. Okay, I'm not sure if I'll have time to do much of the and to do an example, but the idea should be similar to the sequence of limits, to the limit of sequence. Okay? The proof idea should be similar. You write down the outlines and you do the scratch work, fill in the blank, check your writing and whatnot. Under the mapping F is contained in VA. This is a highly verbal description. We're going to translate this into symbols. Okay? But first of all, a picture. All right, so let's visualize the function f using Venn diagram. For that, we need two sets. Okay, so this is R, this is R, and after that, we'll do a graph. This is R. Okay, f maps from R to R. Okay, and this is a point A, and this is a point FA, this image. The definition says for any neighborhood V of f of A, v of f of a, which is visualized as a circle centered at f of a. This is a neighborhood of f of a. And later on, we're going to assign a radius to it. And in fact, let's just do it now, right? The neighborhood, as we know, right? It's just f of a. This is just f of a minus epsilon, f of a plus epsilon. So let's just visualize this open set with a circle with radius epsilon, like this. So this is v of f of a. So everything in here has a distance between f of a that is less than epsilon. All right. For every such neighborhood, there exists a neighborhood UA. So there's a neighborhood on the left as well. So you can think of this for any there exists format statement, this kind of statement, as kind of a challenge response. So I challenge someone, say, this is the neighborhood of f of a. You need to find a neighborhood on the left, right, so that the condition holds. This is like a challenge response format. Yeah, so, right, this is u of a. And u of a has this property that whose image, what is the image? Image means the collection of output. So the image under the mapping f, this notion here, is f of u of a. F of u of a is simply the collection of values f of x such that x is in u of a. So it says the image under the mapping, the collection is contained in v of fa. So that is to say, let me change the color. So f maps the UA set to a set that is completely contained by v of f of a. So everything in the image, okay? We don't know the exact shape. It might look rather general. Okay, so this is the image. Suppose this is the image. Okay. Oops. Actually, you know what? Let's just leave it as a heart, because to indicate this is arbitrary. Okay. So that's the image of UA. Hang on. Maybe we can do that. Push it up like that. Yeah, that's better. Push it down like this. Yeah, so here, this is the f of u of a. I didn't know one node could do that, actually. Here, basically, the image of u of a is completely contained in the neighborhood v of f of a. That's basically what it says. Right, and let's unpack this on the right. So f of u of a contained in v of f of a means if, let's say, y, right, y is in the image, then y minus f of a absolute value is less than epsilon. Right? That's the meaning of y in the neighborhood of f of a. Okay, but what does y belongs to the image mean? What does y belongs to y? But what does y belongs to f of ua mean? So this also just means it's completely equivalent. Okay, it means if, let's say, f of y, because y belongs to not f of y, but rather, so if x is in ua, if x is in UA, then f of x is in f of UA. That's trivial. And f of x would satisfy f of x minus f of a. Absolute value is less than epsilon. And UA, because that's a neighborhood as well, right? You can specify its radius. You can parameterize UA by another radius, say delta. So this is where the famous epsilon delta definition comes from. For every epsilon, there exists a delta. This means if x is x minus a absolute value less than delta, then f of x minus f of a absolute value is less than epsilon. So this is the same as the verbal description. Image is contained by the neighborhood of the function value. So this is our visual one. This is our visual one, and our second visual would be a graph, a visual 2. Perhaps it's more traditional and it's more natural for, say, a high school student. So this is a graph. The idea of a continuous function. It's very similar to the arrow control idea for limit. Okay, so this is a, and this is f of a. So suppose this is a function, y equals f of x, all right? X-axis, y-axis. Okay, so this is a, and the point a, f a. So just we want what? We want the arc. So it's actually, you know what? Let's first draw the error tolerance, right? F of a plus or minus epsilon. Okay, so going up here, this is f of a plus epsilon, f of a minus epsilon. This is such a well-explained topic on the internet. You can find other creators covering it, right? So, for example, Black Pen, Red Pen, and also, well, Dr. Pyam, you know, all those YouTubers who've been doing this years ahead of me. Right? This is such a important notion in analysis that I think at some point most like creators of math at a higher university level, so to say, discuss this, cover it in detail. Now, compare my exposition with theirs. So I was saying that this part of the arc, let me highlight that. This part of the arc satisfies the error requirement. This part of the arc satisfies the error requirement. F of x minus f of a is has absolute value less than epsilon. Right? But we don't need the whole arc. We just want when x is close enough to a. When x is close enough to a, then the error criteria is satisfied. And of course, this is achievable. So this little piece of red arc here, this red arc here would correspond to v of f of a. V of f of a, okay? So this is v of f of a. But now we just say, oh, I just want x to be when x is close enough to a, the graph would be a part of this red arc. When x is close enough to a, so here, for example, when x is in this range, this is a minus delta, a plus delta. So this way, we only care about this part of the arc. Let me just highlight that. Is with a green arc. So this is a part of the arc that we care about. And what is this green arc? This green arc corresponds to the image. of UA, f of UA. Okay, so let me highlight that. This is f of UA, and this is UA in a definition. And you can do this for every arbitrary positive epsilon. This book is almost equal to the lectures of my first undergraduate analysis. Yeah, it is, after all, standard material. But Zorich, what distinguishing feature of Zorich, if I quote his exact word, is he decided to not to separate the more mechanical or calculational part of the calculus with the more theoretical aspect. He considers them to be an integral part. So in the Russian tradition, you don't take calculus first and then move on to real analysis. You do it simultaneously. Of course, this is very demanding, but it does highlight the interconnectedness of mathematics, which is great. It's not very easy, and it's very it's very Russian. It's very no nonsense, and just kind of a swim or sink mentality. Okay. It does not seem to care too much about accessibility and user friendliness. If you can handle it, you do math. If you can't, well, do something else. Brutal. But you can't argue with the quality of math. Right? You can argue about the, so to say, the culture and whether this is, so to say, how do I put it, a good way to get people interested in math. But the math itself is very solid, and it's if you have a good teacher, I believe you'll fall in love with mathematics with this book. So what would be the quantifier statement? We have the verbal description, right? So the f continuous at A, okay, this is a statement. This can be written as follows. For all neighborhood f of A, why did the Russians develop the different tradition? Well, it's a good question. It can be the topic of a video essay, actually. I'm pretty sure there are Russian viewers in chat, they can pitch in. But I think it has to do with, first of all, just the fact that the country is rather isolated for various reasons, and researchers have to collaborate around themselves. You know, you can't really afford to pick, oh, I'm only going to do applied mathematics, I'm going to only to do pure mathematics. It's often not, you don't have the luxury of doing that. So in response, they have this hyper-integrated approach, especially for early stage training. Yeah, and also there's a lot of investment from the government during the Soviet era into higher education, math and physics, especially those are related to the defense sector. So, yeah, so another way to write this containment was already hinted earlier, right? So this means for every x in the UA, f of x is in V of f of A. Right, and finally, you have for this one was actually the I didn't give the definition of continuity. I gave the definition of limit last time in my introduction to proof, but this is very similar. So one subtle difference is that in the limit you want x minus a to be greater, also absolute value to be greater than 0, because in the limit you don't want to involve f of a. Whereas in the definition of continuity, you must involve f of a. Okay, a little bit of a subtlety there. Okay. Okay, so that's the notion of continuity. And to do a proof, you know what? Because we only have 8 minutes left, let's do a proof. Now, there's so many different ways to write this equivalent definition. You can, first of all, I recommend you go read the section. There are several pages dedicated to explaining the notion in various ways. I wish it has more diagram like this one, but you can draw it yourself. No, I'm not a math professor. No, I'm not. I work in the industry, but I like math. So, and I like talking about math, and I like learning math and teaching math. So, just not in a academic environment, I suppose. I mean, I have nothing against it. I'm not like some kind of hipster, right, saying the academia is corrupted or anything. I figured I have more freedom this way. I can read whatever book I want. I have no publication pressure, that kind of thing. Nothing against academia. So, anyway, don't get me wrong. I know, it's the internet after all, right? Whatever you said can be interpreted and misinterpreted, so I just want to put that disclaimer out of the way. So, here, let's do a proof. Should we do a trickier proof or easy one? Should we do an easy one or trickier one? Actually, you know what? Because we just discussed the definition of limit, right? Why don't we combine the two and give a theorem and says, which is the sequential characterization. This is also quite useful, and it combines both topics. I like it, characterization. So, sequential characterization of continuity, okay? It says the following. So, the two are equivalent, or f of x is continuous at a, at x equals a, if and only if for any sequence, for every sequence xn such that xn converges to a, f of xn converges to f of x. Isn't that cool? So that's a sequential characterization of continuity. And before we prove this, here we have a cool application of it. Perhaps I probably don't have time to fully prove it, but the proof would involve showing both direction. It's if and only if, so you have the if direction, aka this direction. The if direction is actually backward, okay? If direction, the only if direction is forward. And an application for that, a quick application for that, is to show a function is discontinuous. The quick application for this is actually a discontinuous, for showing discontinuity. Why is that? Because it's simply because of the negation. It's simply because the negation of the definition of continuity is rather involved. It's not very easy to work with. Okay, we'll talk about the negation of quantified statement in our next actual intro to proof class or session or live stream, whatever you want to call it. Showing discontinuity is easier with a sequential characterization. For example, we want to show that sine of 1 over x is discontinuous. At x equals 0. So what do? We can pick two sequences, xn, yn, that both converge to 0, but their image under the function is not the same. And this is the idea. So say let's gonna pick xn so that sine of 1 over xn is constant 0, and pick yn such that sine of yn is constant 1 for all n. And at the same time, xn and yn would both converge to 0. And this is doable because you can just pick the special values of sine and sine to achieve that goal. So to see this, pick xn to be the reciprocal of the zeros of sine, 1 over pi n, 1 over n pi, okay? And of course, this satisfies xn tends to 0, and sine of 1 over xn, sine over 1 over xn is just constant 0, of course, which converges to 0. And you pick yn to be the reciprocal of when do sine achieve maximum? Well, half pi plus 2n pi. This way yn tends to 0, and sine of 1 over yn is a constant of 1, which also, of course, converges to 1. So they aren't the same, and this violates the sequential characterization, and hence, therefore, sine of 1 over x is discontinuous at x equals 0. And this is usually the most efficient way to show discontinuity, rather than showing the negation of the definition of continuity, because the negation of continuity is rather involved. Right? So yeah, this is very common for showing discontinuity. So what do mathematicians in industry do? Build models, very much. Build models, analyze data, that kind of thing. Yeah. Well, I mean, ego. Sorry, this is very much an anomaly. This is very early for me, right? I started at 7 a.m. Yeah, as n tends to infinity. The thing is, if you write a sequence limit, it only means when n tends to infinity. Okay? When you write xn tends to a, this means the limit of xn equals a as n tends to infinity, because there is no such thing as, say, the limit of xn, n tends to a finite number, say n naught. Say n naught, if n naught is an integer, then it's just x n naught. So it's trivial. So it's just the evaluation. Okay? So when we write xn right arrow to 0, we always mean the limit of xn as n tends to infinity. So because n tends to infinity is by default, you can not write x tends to infinity. You can write that, of course, but you can ignore it. You can omit it. Okay. All right. So yeah, that's it for today. I really wanted to, perhaps not this week, but next week we'll catch up with Intro to Proof. We'll do more direct proof and start with indirect proofs.
And later we'll do a more specialized proof technique such as induction. All right. So, but yeah, this is me signing off. Okay? This is introduction to proof / explanation of continuity and limit, introduction to analysis stuff. Hopefully